Hi students, good morning. So today I would like to discuss about the testing of transformers, especially open circuit test and single phase transformer. We know that there are two different tests that are conducting on the transformer to determine the core losses and copper losses of the transformer. So the first test is open circuit test. By conducting that open circuit test, we can measure the complete core losses of the transformer. See, there are two main objectives to conduct this open circuit test. The first one is we can measure the open circuit. We can measure the complete iron losses of the transformer or core losses of the transformer, because we know that iron losses are equal to core losses. And we can also determine the shunt branch parameters of the transformer. So we know that what are the shunt branch parameters? That is core loss resistance RC and magnetizing reactance XM. So these two parameters can be calculated from the readings what we are obtained from the open circuit test. So we can extract those two values, that is RC and XM, by doing some mathematical analysis. So these two are the main objectives to conduct the open circuit test and single phase transformer, right? So objectives are over. Now what are the conditions that are required to conduct the open circuit test? So is there any conditions are required? Definitely required. So before conducting the open circuit test, first of all you have to check which winding is low voltage winding and which winding is high voltage winding. So low voltage winding means, that means generally we are calling it as LV winding. High voltage winding means HV winding. So, to conduct the open circuit test, always it is preferable to make open the high voltage winding, and we need to connect the complete equipment on the low voltage side. Why we have to do like this? Because see, while conducting this open circuit test, it is required to apply the rated voltage of that particular winding. Suppose if it is LV winding, let us consider one transformer. The transformer is having a ratio of 11 kV by 440. Generally we have this type of transformers in our substations. So 11 kV by 440. So high voltage winding is 11 kV, low voltage winding is 440 volts. See, if you observe this, if you want to test this transformer, it is always better to apply 440 volts instead of 11 kV while testing, because this transformer first of all manufacturing at one company, and in that company itself it has to be tested and later it will be dispatched. So it is always preferable to apply less voltage than high voltage to the transformer as well as personnel also. So it is very important. So here we have two voltages, 11 kV and 440. So to conduct open circuit test, it is required to apply the rated voltage of that particular winding. So we have 11 kV winding and we have 440 volts winding, one high voltage winding, one low voltage winding. So it is better to apply low voltage rated voltage than high voltage of high voltage, that is rated high voltage. And it is very safe to the personnel also, that is the person who is conducting that experiment is also in safe mode when we are operating with 440 volts and comparing with the 11 kV. So this is the first condition, that is this test should be conducted on low voltage side and high voltage side should be kept open. This is the first condition. And of course the one more condition is there. I already discussed the point in the previous. So what is that means? So this open circuit test should be conducted at a rated voltage condition and a rated flux condition. Sir, why we have to apply rated voltage and rated flux? We know by conducting this test, we have to measure the complete iron losses of the transformer, otherwise complete core losses of the transformer. So we know that these core losses are proportional to the rated voltage and rated flux. So that is, so if you apply less amount of voltage, you can get some portion of iron losses. If you apply less percentage of flux, then we know that iron losses and or core losses are produced only due to the flux only. So if you apply less amount of flux, corresponding to that flux, reduced amount of iron losses are only existing. So it is but in the objectives we discussed that was the main objective of this test is to measure the complete iron losses of the transformer, not the fraction of iron losses and not the fraction of core losses. So we strictly mention that is we have to measure the complete iron losses of the transformer, right? So now coming to the conditions, this test should be conducted at rated voltage as well as rated flux condition. So once if you apply the rated voltage to the low voltage winding, then our test will be completed. So while conducting this test, what are the other parameters we required? So let us see. From the diagram we can very easily identify this. So if you observe, this one is high voltage winding. This high voltage winding is kept open circuit here. OC means open circuited, and if you observe here, this is the LV winding. This to this LV winding we connected the different equipment, that was those are C, M, L, CB. This is an LPF wattmeter. Why we have to connect LPF wattmeter means, under no load condition the power factor of the transformer is very less. This power it is operating with a very less power factor, that is less than 0.2 lag. So that it is preferable to use the LPF wattmeter than UPF wattmeter here. And one ammeter which measures the current, and second one and last one is voltmeter. This voltmeter measures the how much voltage we are applying to this LV winding. So and before this one is the single phase auto transformer or thermostat. So we have to see, this is the single phase supply. It is applied to the auto transformer by changing this arrow position. That is, in auto transformer we have one particular controlling action is there, that is by changing the position of the knob we can change the voltage that we are applying to the low voltage winding. So now by gradually increasing the voltage to the LV winding, and that is measured by the voltmeter V, and we have to increase the voltage whenever the voltmeter V measures the rated voltage of this LV winding. Then we stop the experiment and note down the two readings. Those are ammeter reading and this wattmeter reading, because already voltmeter reading is known value, because so that is the rated voltage of the LV winding. So remaining two unknown parameters are ammeter reading and wattmeter reading. Ammeter reading is written as I naught and wattmeter reading is written as W naught. See here it is very clear. So in this table, so voltmeter reading known value and ammeter reading unknown and wattmeter reading unknown. By conducting this test we can measure these two. So with this, whenever the voltmeter shows the rated voltage of the LV winding, there we stopped the experiment and noted down these two values. Now in this table, what are the remaining parameters are cos Y naught. By using mathematical calculations we can find the cos Y naught and the RC, XM and Z naught. So let us see how to extract these values from the mathematical analysis. See, it is very clear. When we are conducting this open circuit test, we taken that is the wattmeter reading is completely only the core loss of the transformer, not any other losses. But actually, to be said strictly, it is wrong. Definitely some percentage of copper losses are also included in the wattmeter reading. So but we can neglect. Why we are neglecting those copper losses? Because I'm explaining. Let me explain. So under no load condition, the current drawn by the transformer is 5 to 8% of full load voltage, full load current. See, that is suppose if you consider 100 ampere rated current transformer, so under no load condition, it is drawing only 5 to 8%, that is 5 to 8 amperes current only it can draw. So what are the copper loss? Copper loss are I square R losses. So copper losses or I square R loss means actually those losses are complete copper, full load copper losses are 100 square into some resistance. But here only there is a 5 to 8% of full load current, that is 5 to 8 amperes current is passing corresponding to this 5 to 8%. So comparing with the full load losses, only 10% of losses only existing in the wattmeter reading. That is, so wattmeter reading is equal to, see here, if you observe this area, this statement, W naught is equal to, W naught means wattmeter reading is equal to P core, that is core losses of the transformer, plus a small percentage value of copper loss. Why we are mentioned small percent means, because here the current drawn by the transformer is very less, so corresponding to reduced current, the copper losses are also very less, so that dominant core losses plus small percentage of copper losses we have in the wattmeter reading. So that is the reason. So we can neglect the copper losses of the transformer, and then so W naught is equal to P core only. That is, wattmeter reading can be taken as core losses of the transformer. Please remind, that is core losses are, iron losses are, both are same. Copper losses are different. So now let us move to the mathematical analysis, how we are extracting the RC and XM value. So we know that wattmeter reading is nothing but the, what is the input power we are given to the transformer, right? What we are given, the input power to the transformer can be measured by the wattmeter. Those are completely converted into losses, because there is no output. There is no output at all when we are conducting open circuit test, because the secondary side is open circuited, so we cannot get any output. So the power what we are given to the primary winding is completely converted into core losses. So of course small percent of copper losses are also there, we can neglect it. So P core is equal to, what is the input power? We are giving V1 voltage, and current passing through this transformer is I naught into cos Y naught. So P core is equal to, see, this is the relation, P core is equal to V1 I naught cos Y naught. From this equation we can write cos Y naught is equal to W naught by V1 I naught, because P core is equal to W naught. So W naught is nothing but wattmeter reading, V1 is nothing but voltmeter reading, I naught is nothing but V1 is nothing but voltmeter reading, I naught is nothing but ammeter reading. So cos Y naught is equal to wattmeter reading by voltmeter reading into ammeter reading. So it can give the cos Y naught. Once you know the value of cos Y naught, it is very easy to write, obtain the value of phi naught, that is cos inverse of W naught by V1 into I naught, that can give the phi naught. Once you know the value of phi naught, later you can write the sin phi naught also, because phi naught is there. Suppose phi naught is equal to, if you get 30 degrees, cos inverse of W naught by V1 by I naught. So then once you know the value of phi naught, sin phi can be easily calculated. So if you have these two values, that is cos phi naught and sin phi naught, it is very easy to measure the values of core loss resistance RC and magnetizing reactance XM. So we know that RC is equal to V1 by I naught into cos phi naught. This is nothing but real part of no load current I naught. I naught cos phi naught is called as IW, that is working loss component of no load current. Once again I am telling you, I naught cos phi naught is written as IW. This is working component current, and because it is the real part of I naught, and another parameter is I naught sin phi naught. This is imaginary component of no load current. This is reactive component. See, that is I naught is not a scalar vector, it is not a scalar value, it is a vector. So I naught can be written as I naught cos phi naught plus j I naught sin phi naught. So RC can be obtained by V1 by I naught cos phi naught, and XM can be obtained by I naught sin phi naught, because see, if you observe here, so the equivalent circuit of the transformer under no load condition, see, this is open circuit secondary side, so there is no current passing through here, and this is core loss resistance RC and magnetizing reactance XM, and we are applying V1 voltage. With this V1 voltage, the current passing through this transformer, primary current I1 is equal to I naught only, because here there is no load, and so therefore there is no I1 dash or I2 dash. So what is the current we are given is completely no load current only. So primary current is equal to no load current, and this no load current is passing through these two branches RC and JXM. See, if you observe here at this node, this I naught current is divided into two components, IW and IMU. So if you want to find the value of RC is equal to V1 divided by IW. What is IW? It is the real component of I naught, right? Because it is resistance and it is reactance. So real part of I naught is IW. So IW is equal to I naught cos phi naught, and similarly IMU is equal to, that is IMU is equal to imaginary part, that is reactive component of I naught. So now if you want to get the value of XM is equal to, see, parallel to this XM we have V1 voltage we have, and the current passing through it is IMU. So V1 by IMU is equal to XM. So what is IMU? I naught sin phi naught. Therefore XM is equal to V1 divided by IMU. Therefore V1 divided by I naught sin phi naught, and similarly RC is equal to V1 divided by IW. What is IW? IW is equal to I naught cos phi naught. So it's very simple. Once again I am telling you, open circuit test should be conducted on LV side, high HV side is kept open. Then there are two objectives for conducting this test. First one is measurement of core losses, complete core losses, and the latter one is we have to calculate the core loss resistance RC and magnetizing reactance XM. It's very simple. Now the wattmeter reading can directly give the complete core losses of the transformer, because we are applying rated voltage of the LV winding, and thus this transformer is also operating with rated flux. Once you apply the rated voltage and the rated flux, the losses are complete losses, that is the core losses are complete core losses, not the fractional values, not the percentage of full complete losses. So it can give the complete losses. Next, coming to the remaining two, that is core loss resistance RC and magnetizing reactance XM, those can be calculated. So calculated by the relations, that is RC is equal to V1 by I naught cos phi naught, and XM is equal to V1 by I naught sin phi naught. We already know that V1 is the voltmeter reading, I naught is the ammeter reading. So V1 by I naught cos phi naught, V1 is the voltmeter reading, I naught is the ammeter reading. Cos phi naught can be calculated from the relation. Cos phi naught is equal to wattmeter reading by voltmeter reading into ammeter reading. It's very simple thing. And similarly XM is equal to magnetizing reactance XML is equal to V1 by I naught sin phi naught. So V1 is the voltmeter reading, I naught is the ammeter reading, and sin phi naught can be calculated from the above relation. So it's very simple thing. So our two objectives are completely